Today I'm going to talk about experimental verification. A bit of context first. In our research we want to develop a framework in terms of both concepts and math that we can use to rederive the basic laws so that we have a precise idea of what they describe and when they apply. And the most fundamental object is the idea of a verifiable statement, an assertion that can be confirmed to be true experimentally in finite time. And when some people hear experimental verification, they may object that is really falsification, the hallmark of scientific theories. So let's go through some details and see how I think this works. Oh, and by works, I don't mean, it makes sense to me, it's what scientists do, as if all scientists would agree on something like that. Works for me means I can use those definitions and arguments to rederive mathematical structure, topologies, and sigma algebra that are the foundation of all other mathematical tools used in science, so that you know exactly what they represent, when they're valid, and so on. So let's start with something easy. Consider a statement like, there are 3 apples on the table. This is both verifiable and falsifiable. You look, either there are 3 apples or not. So we call this statement decidable. You can tell experimentally whether it's true or not true. And the issue is not all statements in science are decidable. So consider the statement, extraterrestrial life exists. We can start looking, and if we find evidence, we can confirm it. We can say this statement is verifiable. But if we don't find any evidence, we cannot conclude anything. Maybe we haven't looked in the right spot, maybe our equipment is not sensitive enough, so it's not falsifiable. Now consider another statement like, the mass of the photon is exactly 0. This is not verifiable because we cannot measure the mass with infinite precision. Something like, the mass of the photon is less than 10 to the minus 15 eV is verifiable. And that the value 0 is not important. The mass of the photon is exactly 1 eV or pi eV. They are also not verifiable. It's the infinite precision that is the problem, not the particular value. But note that the mass of the photon is exactly 0 is falsifiable. If we measure that is greater than, say, 10 to the minus 100 eV, we would conclude that the value cannot be 0. So while you can't verify a value from the continuum, you can actually exclude it. And note that for any statement that is verifiable, there is one statement that is falsifiable, the negation. So extraterrestrial life exists is verifiable, but extraterrestrial life doesn't exist is falsifiable. The mass of the photon is exactly 0 is falsifiable, but the mass of the photon is not exactly 0 is verifiable. We could base our framework on either verifiable or falsifiable statement. We choose verifiability because it makes the framework less heavy since you have fewer double negations, less confusing. Now, what's even more interesting is that not everything is either verifiable or falsifiable. Consider the statement, the mass of the photon is a rational number. In any finite precision measurement, there are infinitely many rational and irrational numbers. So even if you keep improving your precision, you're never going to be making any progress. You'd need infinite precision, which you can't have. So the statement, the mass of the photon is a rational number, is undecidable. We won't be able to say anything about it experimentally. Yet, this statement is part of our scientific theories. So we can think of a scientific theory as just a collection of statements of things it will predict, either to be true or false. And some of these will be decidable, some verifiable, some falsifiable, some only somewhat verifiable, and some completely undecidable. You could have a theory that is only made of decidable statements, but this is a very special case. If you have a continuous quantity, for example, your guarantee is that not all statements will be verifiable and that some will be undecidable. What about a theory as a whole? Can we verify or falsify a whole theory? Well, here it depends on what you mean by that. If you say that finding some experimental evidence that contradicts a theory makes it wrong, then I'm afraid that all theories are wrong. For example, we know that Newtonian gravitation does not predict correctly Mercury's perihelion precession, yet we still teach it and use it. We know it is valid only within a certain realm of validity. One issue is that we may not have a clear idea of what is exactly the realm of validity, and that is why in our project, Assumptions of Physics, we try and make those underlying assumptions explicit. But many theories in physics, engineering, economics, and so on have explicit assumptions and approximations. So if you work aside those regimes, you don't complain that the theory is wrong. It's your own fault for using them outside of those assumptions. Okay, say we limit ourselves to the approximation regime, where the theory is supposed to be valid. We will have some predictions there. We can test the positive predictions of verifiable statements, and we can test the negative predictions of falsifiable statements. Can we check them all? Well, the issue here is that we can only make finitely many measurements in finite time. So we can start making tests, but if the theory contains infinitely many statements, and any theory that has continuous quantities will have infinitely many statements, we can never test the whole thing. The only thing we can do is keep testing until we find something that does not agree. So the statement, these infinitely many statements agree with experimental data, is not verifiable, but falsifiable. Hence the idea that scientific theory have to be falsifiable and not necessarily verifiable. But this is also kind of misleading. If you have a new theory that agrees with the old one on all statements that have already been tested, and you test a new statement and you see that it does not agree with your experiment, then you can clearly throw out the whole thing because it's not useful. You would just use the old theory. But if you have a theory that has been working well, like Newtonian gravitation, and you find some things that it does not predict well, you don't throw away the whole thing. You keep track of the things it doesn't do well, and you do more research because maybe there are different effects that you haven't considered, and you keep a note saying, okay, in those regimes, it does not seem to be working. So you either temporarily or permanently restrict the realm of validity of the theory. So to sum up, scientific theory are collections of statements. Some are verifiable, some falsifiable, some both, they're decidable, some neither. Some are completely undecidable. This structure is actually captured mathematically by topologies and sigma algebra. A theory as a whole has a realm of validity where we expect it to be consistent with experimental data. While we must be able to generate the whole theory from a set of verifiable statements, this set might be infinite, so we can't verify the whole theory, only an ever-increasing part. So we are only guaranteed to be able to find disagreement with experimental data and never complete agreement. So the best we can say is the theory so far is in agreement with experimental data. So that's where I am at, and I hope this helps.